The purpose of vectors is, before, when we dealt with vectors before, we actually dealt with this here, right? So let's say we had a force going this way of, let's say, 500, and then a force going this way of, let's say, 800. The resultant is always from the starting point to the ending point. So this would be your actual resultant vector or resultant force. And you use Pythagoras to get that. Okay, so it's very simple and very easy to understand. Hopefully, nothing here is catching you out, is it? It's very simple. Right, so 943.4 newtons. Now, in this year's vectors, what we need to understand, we aren't worried about creating this diagonal vector. We are worried about breaking that diagonal vector up. So for example, just to make sure we are okay, let's say we had this same vector. Let's do this. Let's say we had a vector here, let's say 250 newtons in this case, at an angle of, let's say, 30 degrees, right? So if it's at an angle of 30 degrees, what we're going to do is we are now going to create a vector. So it's a force in the x direction, and this is a force in the y direction. Okay, so we always do it in that form. First we go in the x, and then we go in the y direction. So first in the x and then in the y. So here what we're going to say is that the force in the x direction is what we're looking for. Now, you must not forget last year's trigonometry, right? So it's very important to understand, if we're dealing with the adjacent side, we must deal with cos. So you see, we're dealing with the adjacent side and the hypotenuse. So we must deal with cos. So here, to do this, you can do it the long way and say, oh, okay, I know that cos of 30 is equal to adjacent, which is fx, over the 250. And then fx is actually just 250 cos 30. Now that's important to know, is that we always deal with the angle between the x-axis and our vector. That's always the angle that we deal with, angle between x-axis and vector. So here, in this case, if you want to know what is this, the force in the y direction, it's going to be, we're going to use sine for this case, right? So why am I saying we're going to use sine? Because here, this is the opposite, and we know we have the hypotenuse. So obviously we must use sine. So here you can say it's sine of 30 is equal to opposite, which is fy, over the 250. And then we're going to have it as fy is obviously equal to the 250 sine 30. So don't forget, your components are super important for you guys to understand. And yep, so 250 cos of 30, and that's 216.51 newtons. And then the other one, 250 sine 30. That's half of it, so 125 newtons. Okay, that sorts it out. Okay, so now what I would suggest we do is make sure we understand how these work in different directions, right? So let's say we had one like this here. Say I had one like this here. And remember, the most important thing is make sure that you're working with the angle between x-axis and our vector, yeah, and our diagonal. Okay, so let's say I had this situation. And now I have the following. I'll say that this angle here is 35. Okay, so the first thing I want you to do is please draw the vectors, sorry, not the vectors, the components that go here, right? So draw the components like we did. Remember, these are called components. So you first go on your x-axis and then you go on your y-axis. So just draw the components for this vector here. I'm going to say that this is a force of 350 newtons. And then after that, we can start with resultant. Okay, just send me a picture of what you got though, yeah? In terms of your vector. Okay, I'm hoping we have this here. So force X like that, and then force in the Y direction like that there. Okay, so now to sort this out, very simple. Don't forget, we got to make sure we have the angle between the x-axis and our vector. All right, so sorting this out, pretty simple. If you want the force in the x direction, it's just going to be 350 cos 35. Then force in the y direction is 350 sine 35. Perfect, perfect. So 286. So okay, so 200.75, done. Okay, so now we're done with this first part. And what we're going to do now is we are going to understand what a resultant vector is. Okay, so here, let's just go and write down what a resultant vector is. So a resultant vector, you want to think of it as like displacement in a way, right? It's shortest distance from start to end, but by definition, it is a single vector that has the same effect as multiple vectors acting at a point. That's it. That is what a resultant vector is. Okay, but now what we're going to do is we're going to understand this in terms of calculation. Okay, so to understand in terms of calculation, we're going to start it off fairly simple and fairly basic. So this is what we're going to start off with. Example 1 for resultant vector. We have one here. Okay, so 1 is 200 newtons. Force 2 is 300 newtons. So this is 20 degrees, 40 degrees. Okay, so most important thing here, guys, for you to understand this, is you want to break this up into components, right? So for force 1, we'll draw components this way. First, in our x direction, we first draw it in our x direction, so that's F1x. And then we draw it in our y direction, and that's F1y. Then we do this. We draw it for F2. So F2 first in the x direction, so that's F2x. And then that's F2y. Okay, so now what we're going to do is we are going to calculate the resultant force. Now, how do we do this resultant force? Very simple and very easy. We are going to be introduced to this concept called sum. So if you use Excel, you'll see this particular sum, the symbol, which means the sum. So we don't have to write it like that. All we have to do is we have to say, okay, sum of the forces in the x direction. So just a capital E like that, sum of forces in the x direction, which means all the forces in the x direction. So we have two forces in the x direction here, right? We have F1x and F2x. So now what I'm going to do is I'm going to take a particular direction as positive, because that's very important. You have to choose a direction as positive. So that's important. So sum of forces in the x, got to choose a direction as positive. In this case, I'm choosing to the right because it seems like the right is going to be bigger. So sum of forces in the x direction, choosing to the right is positive here. Now as a vector, because this is going to the right and then this is going to the left, do you think I'm going to be saying F2x plus the F1x, or am I going to say F2x minus this f1x? Do you think I'm going to say f2x plus or f2x minus? Minus, definitely minus. So here, it's going to be f2x minus the f1x. And this is how we do it. So what is f2x for ourselves? We know it's going to be, we have to make sure we know the angles. Yeah, because this is our angle between x-axis and our vector. So now we're going to use cos, right? So we can say f2x is actually 300 cos of 20. f1x is going to be 200, but then cos of 40, this angle between x-axis and our vector. Okay, so that's 128.7. Now, sum of forces in the y direction, we're going to choose going up as positive here, right? We're going to choose going up as positive for this one. And the reason why we're choosing up as positive is because we see most likely you're going to get an answer that is, sorry, you can see up, both vectors here are acting up. So obviously it would make sense to choose up as positive. There's no vector going down, or no component, I should say, going down. All right, so here we're going to say that it should be f1x plus, sorry, not f1x, f1y, f1y plus f2y. Okay, so f1y is going to be 200 sine 40, right? 200 sine 40. And then f2y is going to be 300 sine 20. 300 sine 20. Okay, so 231.16 newtons. Okay, what I do want you to do is just leave some space after this, or if you have space on the side of the page, leave some space on the side. We're going to draw the actual resultant vector after this. So I do want you to leave some space in a bit, right? So the last thing that we have to do is we are going to use Pythagoras, right? So whenever you're dealing with some force in the x direction and then some force in the y direction, because that's what this one is, this is in the y direction, they're always going to be perpendicular to each other. They're always going to be perpendicular to each other, right? Which means we can always use Pythagoras. So here, for the resultant, all you're going to do is you're going to say, okay, the sum of forces in the x all squared plus the sum of forces in the y all squared. And what is that going to be? It's going to be 128.7 all squared plus 231.16 all squared, and done. Okay, so that's 264.57 newtons. That is our resultant. Now, just after this, like I said, leave a little bit of space. We will be drawing the direction of it just now, but for now, it's just to make sure we understand resultant, right? Okay, so let's get started with understanding the bearing. So initially I was just like, maybe we should just do the resultant, but you know what, let's just go and understand the direction part of this entire situation. So what exactly is the direction of this particular vector that we've just sorted out here? So what we notice and what we see is that we obviously are going to the right as positive, and we obviously have a positive answer, so we are actually going to the right. And here we have taking up as positive, and we have a positive answer, so that means we technically are going up. Now, what we need to do here is understand what that vector is going to look like, the resultant vector. So the resultant vector is going to have us going to the right and then up. So what would the actual resultant of that look like? This is what it's going to look like. So we are going to be going to the right, and then we're going to be going up, which means that our resultant
is going to be in that direction. That is our force resultant now. Right? Now that's our force resultant. We know that our force actually in the horizontal is 128.7. So let's go and write that down. That's 128.7 newtons. And then we have this one here as the one going up is 231.16. So wait, 231.16 newtons. And now our resultant. How do we calculate the resultant? We've done that by Pythagoras, and that made life pretty easy for us. What is our actual resultant? We know our resultant is 264.57 newtons. Let me write that a bit better. So 264.57 newtons. All right, now what is the direction? Sometimes in school you can just say, oh, okay, you can draw it in there and you can say it's this particular degrees clockwise or anti-clockwise from the horizontal. However, most of the time in most schools, they introduce the concept called bearing. Now, if you do geography, bearing angles is pretty much intuitive to you. But if you don't do geography, how do you sort out bearing angles? So the way I remember it is I started off with writing the letter B. So writing the letter B means that we are essentially going from the north and we are going in that direction there, which is obviously a clockwise direction, right? So that's your bearing angle, always from the north going clockwise. Okay, so what does that mean for us? All right, so we first got to make sure that we have to introduce a north pole, right? So we need, don't say a north pole, but a y-axis in that sense, right? So what I normally do is I normally just draw a line to say, okay, this is our, I should put it in black. I normally introduce just a y-axis or a north pole, essentially going up like that. And remember, bearing is which way? It's going this way from the north pole. So we need to find out what is our angle, our bearing. That is our bearing angle right there. I should draw it a bit better. That is our bearing angle right there. So in this particular case, my bearing angle itself from the North Pole going clockwise is how much? We're going to figure that out. All we're going to do is we're going to know that this entire piece should be 90 degrees. We obviously know this here is 90. We're going to find this angle here as theta. Let's go and do that there. Now you can use sine, cos, or tan. It doesn't really matter because you have each of your sides. I'll just use tan in case I messed up my resultant, right? So I'm going to say tan theta is equal to opposite over the adjacent. You guys know how tan works. Opposite over adjacent. The so-called TOA thing. So 231.16 all over the 128.7. And what we're going to do now is we're just going to solve for our theta value here. And we are going to get shift tan of, or arc tan correctly said, or 231.16 all over 128.7. And we're going to get it as 60.89 degrees for theta. So we have this as 60.89 degrees. And now to find our actual bearing angle, we're just going to say 90 minus. So we are at a bearing of 90 minus that there, and that's 29.11. So at a bearing of 29.11 degrees is this particular vector. So that vector is at a bearing of 29.11 degrees, and sorts it out. Right. Now, I know you obviously may not get this immediately. So what I want to do is I want to make sure you understand bearing angles in terms of how you identify what the actual bearing angle is. So just quickly, let's just go and do 2 here. So if I said that my resultant is in that direction there, and I need to find out what the bearing is, and I say that this particular angle here, if I say that this angle is, let's say 35 degrees. So what is my bearing for this particular vector here, right? We'll just call this resultant vector, or just resultant force. Now my resultant is in that direction going down that way there. What is my bearing? Remember, my bearing is like you're writing the letter B, you have to go like that and you have to go around. Now it's that same sort of situation here. You got to think of it as like, wait, you got to think of it as, okay, I'm going to be going all the way around till I get to my vector. So I'm at a bearing of how much? Well, let's figure that out. We know that this piece would be 180 degrees, plus the 35. So we are at a bearing of 180 plus 35, which is 215. So my bearing angle here, angle is equal to 215. I'm at a bearing of 215 degrees. That's essentially that. Now, let's change that up a little bit. And let's say we are going in this direction here. And let's say I change it up and I say, okay, well, you know what? This particular angle here is 70 degrees. So what is my bearing angle? At what bearing is this vector going at? Is this resultant force going at? Whoops, I was going to just say R, and then I was thinking about FR, so we just go force resultant. So at what bearing is this particular resultant force? So again, remember, we've got to go this way here around. So let's figure out what this angle here is going to be. That's actually really simple for our bearing angle. We know that the small piece here is going to be 20, and then this piece is 90. So therefore, our bearing angle, or at a bearing of 90 plus 20, which is 110 degrees. Done.